All right, let's see some examples. So here we want to show that that this function here has at least one zero, right? And remember that uh, um, zero is another word for zero's roots. They're also called x-intercepts, right? So that's where the output equals zero, okay? That's where f of x equals zero. Those are called zero's roots, x-intercepts, where they cross the x-axis. That's where the function equals zero, right? So the way I can use the intermediate value theorem is maybe I don't know where this equals zero, right? But I just want to prove that there is a zero. So what I can do is I can say, okay, well, if there's a value where this function is negative, and there's a value where this function is positive, and if it's continuous everywhere in between, that means there has to be a zero, right? If it goes from negative to positive and it's continuous, just like we saw in our graph, if we can't pick up our pencil, we're going to have to cross all those points. So if I go from negative to positive, I'm going to have to pass zero at some point, right? And so that's how we can use the intermediate value theorem to kind of help us to say, hey, well, I don't know exactly where this happened, but I know that it does happen, right? And so that's kind of the idea. So so let's see if we can try to find a value where this is negative, a value where this is positive, and then see if make sure it's continuous everywhere in between. Now, to start out, this is continuous, right? Because we know that this is continuous everywhere, and this is continuous everywhere. There's no limitation on what we can plug in. There's no restriction on our inputs, right? I can take the cosine of any real number, and there's no restriction on that. And definitely, we can take we can plug any real number into x, and there's and that will just be the output, right? And so so anyway, there's no square roots, there's no zeros in the denominators, anything like that, and so this is continuous everywhere, right? So we checked off the fact that that f of x is continuous, and not only on a to b, but it's continuous everywhere, right? Okay, so it's definitely be continuous on a to b. So now let's find a negative. Let's find an output where we get a negative. Okay, so first of all, I know like some basics about cosine, and we haven't done too much trig yet review, but remember that cosine starts at a cosine of 0 is 1, cosine of 90 is 0. So if we're thinking about the unit circle, remember cosine of the x value. So cosine starts at 1 when the angle is 0, and then when you get to 90 degrees or pi over 2, cosine becomes 0, and then it goes back to 1, or negative 1, excuse me, and then back to 0, and then back to positive 1, right? So I'm just going to keep it simple and just say cosine of 0, right? So I know cosine of 0 is 1. So if I take f of 0, then I'm going to plug in 0 for x and 0 for cosine. And so that's going to give me 0 minus 1. Okay? And that equals negative 1. So I just found my a value. So I know f of 0 equals negative 1. All right? So what I just found was my a. So a is 0. That's my input. So from 0 to, and then let's find something that's positive. Let's find an output that gives us a positive value. So remember that we talked about at pi over 2, cosine is 0. So if I plug in pi over 2, if I do f of pi over 2, then I get pi over 2 minus cosine of pi over 2, right? And cosine of pi over 2 is 0. So I'm going to get pi over 2 minus 0, which equals pi over 2. Okay, so what I just found is f of pi over 2 is equal to pi over 2. All right, so I'm just going to put in pi over 2 as my right endpoint. Okay, so from 0 to pi over 2, since I go from negative 1 to pi over 2, there has to be a value somewhere in here. There has to be a value c as an input between 0 and pi over 2 that produces any of these values between -1 and pi over 2, including 0, right? So there must be a value c between -1 and pi over 2 that produces a 0 for this function, okay? So we just proved that that there's a 0 between 0 and pi over 2, right? And by the way, I picked these numbers just because they were kind of familiar and convenient, but you could pick other numbers too. Like you might be able to find another place where cosine, or where x minus cosine x, where that function is negative, and you might be able to find a different place where it's positive. There are infinite amount of both, and so you might have a different interval here that you found, but you can still prove the same thing. Okay. All right. So that's one example of how to use the intermediate value theorem to validate or prove something. Okay, now the second one is kind of getting at how we want to, or the fact that we don't want to overgeneralize the intermediate value theorem, right? We don't want to overreach its boundaries, right? So we can definitely prove that there are values that exist, like we did on 2.36, but we can't always prove that certain values don't exist, right? Like for example, here we have a function f of x that's continuous over 0, 2. So it goes from 0 to 2 in that closed interval, and we know that f of 0 is greater than 0 and f of 2 is greater than 0. So can we use the intermediate value theorem, IVT, to conclude that f of x has no zeros on the intervals 0 to 2? So let's just plot this out to some extent. So let's say that, so we're going from 0 to 2. We have this interval, right? From 0 to 2. And what they tell us is they tell us that f of 0 is greater than 0, right? So that means if this is greater than 0, that means that there's some point on the graph up here above the x-axis, right? So this would be f of 0. And they're telling us that f of 2 is also greater than 0, so it may be up here, right? So over here we have f of 2. Now, so then they're saying, can we say that there are no zeros in this interval from 0 to 2? And that's not the case, right? Remember that we know that we have to cross every point in between f of 0 and f of 2. We know that's the case. But what we don't know is what path we take to get there, right? So we could easily go down below the x-axis, come back up, go below, come back up, right? We could do something like that where we have 1, 2, 3, 4 zeros. So not only do we have, not only do we not have no zeros, but we could have, 4 zeros or even more, right? And so we can't. So don't overstretch the intermediate value theorem, right? We can't exclude anything outside of the range here, outside of this range. But we can say that, hey, there has to be every value within this range that happens at least once, right? So the intermediate value doesn't exclude the potential of points that go above or below f of a and f of b, but it does make sure that you include all the points in between. Okay, so watch out for that. And so the takeaway is, we see what we can do with the intermediate value theorem, but also don't lose sight of what its limitations are, right? What we cannot do with the intermediate value theorem.